Okay, so today we're going to be continuing with our endocrine system. All right, so we're going to start out with a couple sort of review questions about some of the stuff we did last time. So the hormone that we really focused in on, or one of our hormones that we focused in on in our glands, were the thyroid hormones coming from the thyroid gland. Okay, so in this question, I want to make sure that we understand what it meant when we were talking about a calorogenic effect for those hormones, because we were talking a fair bit about the pathway. I want to make sure that we understand kind of the point. Okay, take another couple seconds. Do one more review question after this. Okay. Okay. How we doing? Okay, cool. All right, so we are mostly on the same page, at least for those of you who answered. Okay, so big picture, the reason we are talking about thyroid hormones is that they help regulate metabolism. So they do that by changing transcription rates of mRNA, changing what proteins we make, but that means really that what they're doing is changing the number of proteins that we have in the cell membrane. So changing things like our sodium potassium pump, and changing the number of enzymes we have available. So enzymes, in this case, related to metabolism. We had a big long list of all the things that thyroid hormones do, but through the rest of this unit, including this next section, we're going to repeatedly have like bulleted lists of this has this effect and this effect and this effect and this effect. I recommend to you that it's kind of easier rather than memorizing all of those lists sometimes to think about like the big picture effect, like what is this overall doing? And then just relating each of those bullet points to, okay, like how does this bullet point give us this larger effect, in this case of regulating metabolism. Your mileage may vary on that, but I think it's, at least for me, easier to remember one thing and then just kind of back solve the rest of the things rather than trying to start with all the many things and get towards the point. Okay. So the next one is going to ask you to rank stuff, I think, but we're going to use it as matching instead. So first thing I want you to do is select the hormone secreted by the adrenal medulla, so the inside part. Second, I want you to select the hormone secreted by the adrenal cortex, so that outside shell part. And then I want you to select the option that isn't coming from the adrenal gland. Oop. I didn't mean those to display immediately, sorry. Be confident in your own answers. Okay. So I'm going to use this now as a prompt to talk about this, because now that I'm seeing how it displays the results, I'm suddenly realizing that I'm not exactly sure what it's tallying with those green bars. So these are in the order of those things. So epinephrine, looks like most of you chose first. I assume that's what the green bar hopefully is. So that is coming from the adrenal medulla. So I'm just going to draw our little adrenal gland. It sits on top of our kidney. So drawing a kidney here. Okay. So adrenal gland is one of our endocrine organs. So it has an outside portion and an inside portion. Okay. So the outside part, that shell, is the cortex. The adrenal medulla is this inside part. Okay. And when we're thinking about the inside part, so that's what we're doing first, that adrenal medulla, we're thinking about our sympathetic nervous system. So in our sympathetic nervous system, we have a preganglionic neuron, which is cholinergic because it secretes the neurotransmitter acetylcholine at that first ganglion, usually in the sympathetic chain. Then we have a postganglionic neuron going out to the body usually, but in the case of our adrenal medulla, we have that preganglionic neuron going all the way in, and we have a modified postganglionic neuron called the chromaffin cell in the adrenal medulla, part of the adrenal medulla, okay? And postganglionic neurons in the sympathetic nervous system generally release norepinephrine, but these chromaffin cells with their special modifications release 80% epinephrine. So this is where most of your epinephrine comes from. So epinephrine, epi is like EpiPen, that is epinephrine, okay? 80% norepinephrine, 20%. Okay, so that's what's coming from the adrenal medulla. Versus from the adrenal cortex, we have a bunch of corticoids, right? So we have mineralocorticoids, we have glucocorticoids. The main one we were interested in for our purposes of this unit anyway was cortisol. So cortisol was a glucocorticoid coming from the adrenal cortex, right? That's why it starts with cortisol. Okay. So we think of this as a stress hormone. It's regulated by the hypothalamic pituitary axis. So we've got a whole flow of tropic hormones that lead us to the production of cortisol from the adrenal cortex. So from the hypothalamus, we had the tropic hormone, the hypothalamic tropic hormone, CRH. And that goes down into the anterior pituitary, where the anterior pituitary secretes ACTH. Okay. That then swims down all the way through our bloodstream to the adrenal cortex, where eventually the adrenal cortex secretes cortisol. Okay, so that's why our third answer, not part of the adrenal gland, is ACTH, because that is coming from our anterior pituitary. So it's like part of the picture, but it's not coming from the adrenal gland. Questions about this kind of setup with the adrenal gland? And we can practice some of these pathways more as we continue through this unit. Okay, so this was where we left off. We were thinking about the role of cortisol, specifically in our stress response. So when you stress out or you're reacting to a stressor, we have a suite of reactions that your body is going to have, which we call general adaptation syndrome. It's this reaction to stress. So in this reaction to stress, we have increased cortisol secretion, which is why we think of cortisol as a stress hormone primarily, even though it does do other things like help us wake up in the morning, and then with lower levels, let us get sleepy at night. When we're stressed out, we know that the sympathetic nervous system, that sympathetic branch of the autonomic nervous system, is the fight or flight part. Right, so that's also part of general adaptation syndrome. You'll expect to see heightened sympathetic activity. The sympathetic nervous system links in to the adrenal medulla and those chromaffin cells, which is where we see secretion of epinephrine, which is also known as adrenaline. I think that's more of a British term, but they're the same thing. So epinephrine secretion is also part of our stress response. So actually both parts of our adrenal gland would be active in this general adaptation syndrome. So if we think about it from the adrenal gland's perspective, the adrenal medulla is producing that epinephrine in response to the sympathetic nervous system. The adrenal cortex is secreting cortisol, not because of the sympathetic nervous system, but because of that pathway coming down from the hypothalamus and pituitary. We also see some other hormones mainly related to blood pressure involved in general adaptation syndrome. So ADH and angiotensin 2, when we talk about blood and vasculature and blood pressure and kidneys, we'll talk about how those two hormones are related to maintenance of blood pressure, which allows you to have sufficient blood flow in response to stress. So all of this, the point of it is to allow fight or flight. So this is similar to what's going on with the thyroid hormones. So the thyroid hormones aren't part of general adaptation syndrome. They're a more metabolic process. But this is the way that in these fight or flight situations, we're going to be mobilizing energy stores in addition to maintaining blood pressure so that we're able to fight something off or run away. Yeah, so this is more of a response to an immediate stressor, whereas thyroid hormones, you kind of have a like longer term effect, right? That's kind of going all the time, hopefully. Okay, so this brings us to the pancreas. So this is our next gland. So the pancreas, you're going to see tucked kind of behind the stomach in the body. So you won't see it in lab this semester, but if you stick around for A&P 2, you will see it in the spring. All right. So glands really are kind of yellow looking. They honestly kind of look like fat. You're going to see that those tissues look somewhat similar, but they're not. They're their own special type of tissue. So we're going to have a number of different types of cells in the pancreas. So we're going to have both an exocrine part and an endocrine part. Okay. So up here at the top, this is referring to the exocrine pancreas, but we're in the endocrine unit. So the difference between those two things is like where our secretions are going. So when we talk about the exocrine pancreas, we're really going to be coming back to this mostly in our digestive unit, actually, because one of the jobs of the pancreas is to secrete fluid and enzymes that's going into your gut, right? That's why it's physically located there. So you're going to have secretions from the exocrine cells of the pancreas going into your small intestine, helping you break down food, helping you kind of change the pH a little bit, maintain that, entering the digestive tract there. So exocrine stuff goes into a duct and is physically traveling to kind of like a local area. Endocrine stuff is when we're thinking about hormones. So endocrine function involves these hormones, these signaling molecules going into the blood and then traveling through the blood to go to other parts of the body. So that's the difference here between exocrine and endocrine from a functional perspective, like a what they're doing perspective. But we can also look at the, okay, where in the pancreas are we getting these different products from, right? So the bulk of the pancreas, so like most of the body of the pancreas is made up of exocrine cells, right? Exocrine stuff. And we'll talk about the structure of those cells and ducts and stuff when we get to our digestive system. But that's what you're looking at, like here with your darker pink, right? Those are exocrine pancreas. Okay? When we're looking at the endocrine part of the pancreas, we are going to be zooming in on these lighter parts, actually. So this little patch here is a patch of endocrine cells called an islet of Langerhans. So islet, think like these little islands in the pancreas, okay? So they're going to be smaller, but they're super important when it comes to hormones, and specifically hormones that are going to help us regulate what you're doing with the products of digestion. So we're going to be talking a lot about how these hormones let you get glucose into your body and how they let you get glucose kind of out of cells, like what you do with it. And we'll zoom in on that in a second. Okay. So we're looking at the endocrine pancreas in cartoon form. It may look something like this. So we're zooming in on that islet of Langerhans, so that lighter pink part. And we have drawn some exocrine pancreas stuff around the outside. So we got some duct cells. We got some exocrine cells, some acinar cells. On the inside is where we have our endocrine cells. And we're going to be looking at mostly two types. So the two most important types for our purposes are going to be the alpha and beta cells. The delta and F cells do also exist. So we don't want to think there's only alpha and beta cells in there, but we're going to be really focusing in on the function of insulin and glucagon when we're focusing on the endocrine pancreas. Okay, so our alpha cells are here. Okay, so these alpha cells are the blue ones. They're going to be secreting glucagon. Yeah. And our beta cells are going to be secreting insulin. Okay. So hopefully you've heard the word insulin before, associated with diabetes, right? Some people need to give themselves insulin injections. And hopefully after this next section of the unit, we'll kind of understand why. Okay. So alpha cells, glucagon, beta cells, insulin are going to be comparing and contrasting these two hormones for the next little while. Delta cells are secreting something called somatostatin. F cells are secreting something called pancreatic polypeptide. And we're not really going to be thinking about those for the purposes of this course. We're going to be thinking about insulin and glucagon. And in order to do that, we need to think about these two states called the absorptive state and the post-absorptive state. These are going to be related to metabolism. So your body is basically going to have periods of time where it is resting, digesting, trying to get stuff that you've eaten into the body. And there are times when it's going to want to use those energy stores to continue functioning. Okay. And that's what we're talking about when we're talking about absorptive and post-absorptive. Okay. So our first compare and contrast here between absorptive and post-absorptive. So during the absorptive state, our big picture goal is to take energy that we're taking in, like in the form of food, and to store it in macromolecules in our cells, right? So we're trying to get energy into our cells and store it for later, okay? So this is an anabolic process here. So we're going to be storing in macromolecules. During the post-absorptive state, it's the opposite, right? So if during the absorptive state, we absorb stuff into cells and we store all that energy in our cells, during the post-absorptive state later on, we're going to want to use that energy. The point of storing it was to use it. So during the post-absorptive state is when you're going to see these energy stores being mobilized, so broken down and set out to the rest of the body. So I got a summary slide for each of these, okay? So when we're talking about the absorptive state, if we do a comparison about the energy you're taking in, like from your environment, so think food really is what we're talking about, versus energy you're putting out, right? So think about metabolism, think about making and using ATP, right? Going on a run, something like that, right? That's your output. In the absorptive state, the stuff you're taking in, the energy you're taking in is greater than the energy you're putting out. So on net, your body is gaining more energy during the absorptive state. Okay. When we think about the absorptive state, really when we think about both of these states, we're going to be thinking a lot about glucose. The reason we're thinking about glucose is that's the primary energy source for our cells. Our main type of metabolism is glucose metabolism, right? Glucose oxidation, where we take glucose, break it down, get that ATP out of it so that we can use it for our cellular processes, okay? So during the absorptive state, we're going to see that we have lots of glucose around, right? Because our absorptive state is pretty much going to happen right after you've eaten something, right? So when your food essentially hits your intestines, starting around then, right? Once the food is in your body, this is when we're going to be starting our absorptive state. We've eaten any carbohydrates, right? You're getting that glucose in your bloodstream as your intestines absorb it. So there's plenty of glucose to go around. So really all of our cell types are just going to be using that glucose to make ATP for whatever cellular processes they are doing. Any extra nutrients, we're going to store them, okay? So we're going to use glucose in our cells, and hopefully, since we're in the absorptive state, by definition, we're going to have extra. So in the liver and muscle, we're going to take extra glucose and string it together, essentially like beads into glycogen. And we're going to take lipids and store our lipids in adipose tissue, which is fat, as triglycerides. So our main molecule of like fats and oils. And so we're taking excess nutrients, storing them so that we can use them later. Here's a flowchart of what's going on here. Okay, so in our absorptive state, this is what we're looking at. So we start out by absorbing small nutrients into the blood. Okay. And once we have these nutrients, they've come through the intestines, you got them in your blood. This is the absorptive state. Okay. Things you might have that you absorbed into your blood: glucose. So we got our carbohydrates, fatty acids. So any fats, oils, triglycerides, lipids, right? Also coming from your food. amino acids. So we're thinking like proteins, right? We've broken down some proteins into smaller chunks. So we'll have some amino acids in the blood. So our glucose, we're going to take, and in most of our body cells, we're going to just harvest the ATP in that glucose. So the energy here is ATP, right? That's our cellular form of energy. Same thing. Okay. We can use that ATP to do whatever the cell needs to do, right? We can use it to pump sodium out of the cell, potassium in, right? The sodium potassium pump runs on ATP. We're going to see we need ATP for muscle cell contractions. There's all sorts of stuff that your cell does that need ATP. In your liver and muscle, we have specifically a portion of the storage piece going on here. So in the liver and muscle, we're taking glucose monomers, right, and stringing them together into glycogen. So this is a storage molecule for carbohydrates that we see specifically in liver and muscle. Finally, glucose. Some of it we're going to need in the liver and adipose tissue to help us make that glycerol backbone so that we can make triglycerides to store as fat, essentially. Fatty acids themselves. So fatty acid chains, right, were those long hydrocarbon chains. In a triglyceride, we had 3 of them attached to a glycerol backbone. That's why they were triglycerides. We also saw them in our phospholipids. So our phospholipids had 2 fatty acid chains. That's part of what's making our cell membrane. Okay. So during our absorptive state, we're taking those fatty acids to the liver and adipose tissue. We're going to take those fatty acids, grab some glycerol that we're going to make from the glucose, because glycerol, that backbone, is a carbohydrate, an alcohol, really. And we're going to make it into a triglyceride. So we're making this nice little flag structure. So that's the form we're going to store our fats in our fat tissue. Finally, our proteins. We're going to take our amino acids, which are our broken down monomers of our proteins. The liver can actually convert some of that to fatty acids and shuffle those over to this triglyceride production. So the liver can kind of turn turn protein into fat. Okay. And in muscle cells and other cells, we're going to take those amino acids and build them up into big proteins again. So we digested some form of protein, which means we had to break it up into amino acids so it can fit in our blood. So we got small enough chunks. Once it's in a muscle cell or another cell, we can build it back up into a new protein that your cell needs. Okay. So that was the absorptive state. So all of that is what's happening when you eat something. You have lots of energy available. You're building up energy stores, as well as using glucose for whatever you happen to be doing. Then we're going to shift into the post-absorptive state. So as you're using up that glucose, pulling it out of the blood and storing it as glycogen, taking those other nutrients, putting them in storage molecules as well. So like your proteins or triglycerides, right? Your blood levels of those nutrients are going down, right? Because they're coming out of the blood and you're pulling them into cells and doing stuff with them. Okay. So after a certain point, you no longer have tons of glucose swimming around in your bloodstream. And this means that you're going to shift into a different state. So during the post-absorptive state, this is after you've eaten, right? Probably a couple hours, right? Now, you no longer have energy coming in from digestion, but you are still thinking, or potentially if you're asleep, dreaming, right? Walking around, you're doing stuff, right? So this is the post-absorptive state. You're using more energy, your output is greater than the energy input during this time. Okay? So this is going to be characterized by the fact that we no longer have all this glucose freely flowing around because we just stored it during the absorptive state or used it. So we're going to keep any glucose that remains very specifically for the nervous system. So that brief little summary of glial cells and the brain that we did at the very end of our last unit, right? One of the things that we spoke about was that the brain really needs glucose. It mainly can only use glucose for energy. Other cells in your body can work with other things, but brain really needs glucose, okay? So during the post-absorptive state, any glucose that we have, we are going to be keeping that for the nervous system because the nervous system is picky, basically. Nervous system is pickier than your other organ systems, so we're feeding it whatever glucose we have. Other tissues, less picky, so other cells can break up fatty acids or other things and use those for energy. During this post-absorptive state, any of those storage molecules that we've built up, we're breaking them down and using them for energy. So more formally, we're saying stored nutrients are broken down and mobilized. So we're breaking up whatever we stored, putting it into the blood, using it so that we can continue functioning normally. Okay. So in flowchart form, what's happening during the post-absorptive state is we have all these stored macromolecules that now we need to use, right? We were storing them up for just this situation. When we're using more energy than we're taking in. Okay, so we can break up what's happening by cell type, so by location, essentially. Okay, so in general, in our muscle cells and some other cells, we're going to be taking proteins, breaking them up into amino acids. So we're chopping up proteins into their monomers, the amino acids. Okay, those amino acids are going into the blood. Okay, so you can see during this post-absorptive state, as we're breaking up those macromolecules, we're seeing a rise in amino acids in the blood because they're coming from this breakdown of those proteins. Okay, in our adipose tissue, what we were storing was those triglycerides. So we built them up before. Now we're breaking them down. So when we break them down, we're going to get 3 fatty acids and a glycerol. Okay. We're also going to have those fatty acids going to the bloodstream. Some of them are also going to go to the liver to make ketones, which are an alternative form of energy for your body, basically. The glycerol is partially going to be turned into glucose. We have a couple ways that we're getting glucose into our bloodstream in this situation where we're starting out with low glucose. Okay, so we're going to see some of it is we're going to be building it from other molecules. So we're building new glucose, which is gluconeogenesis. We're going to be taking glycogen stores and we're going to be breaking those down. So in the liver, we're going to break that glycogen down directly into glucose. In muscle, we've got a little bit of an intermediate step. That glycogen has to go through a step where we first turn it into lactate and pyruvate, but still we're going to be making glucose. Okay. All right. So now we want to think about what's happening with these things that we've put into the blood by breaking down those molecules. Okay. So during the post-absorptive state, we're seeing all of these components, all of these nutrients on the rise in the blood because we're mobilizing them from their storage locations. So in any cell that's not related to your nervous system, we are going to see use of something other than glucose for energy, right? So there's no arrow from glucose over to non-nervous tissue, but there are arrows from everything else. And in our nervous tissue, that's where we're really going to be using this glucose that we were making from other stuff, or any glucose that we had left. Okay? We're using that for normal glucose metabolism. Ketones are a kind of exception to this. They can also be used a little bit by your nervous system. Not a major emphasis of this course, but it does happen to be true. Okay. So those are the states and kind of the point of the absorptive and post-absorptive states. So now we want to think about, how does this happen? How are we regulating this? Why? Right. So this is where we think about those hormones, insulin and glucagon, that were coming from the endocrine pancreas, from those islets of Langerhans. Okay. So each of those two states essentially has a hormone that's in charge. So insulin is going to be in charge of your absorptive state. So insulin is going to be in charge of that state where you've eaten and you are going to be storing up all those excess nutrients. Glucagon, coming from those alpha cells in the pancreas, is going to be our hormone of the post-absorptive state. So it's kind of in charge of making sure that you're starting to break down those storage molecules and get them out to the body so that you can continue functioning normally. There are some other bit players in this picture. So epinephrine, coming from that adrenal medulla, does play a little bit of a role in here, as does your sympathetic nervous system more generally. But for our purposes, what we really want to understand when we're thinking about absorptive and post-absorptive is mainly this compare-contrast between insulin and glucagon. So they have opposite effects, and they are present in opposite states. Okay. So we just talked about the absorptive state, post-absorptive state, and now we want to kind of link that up with this new information that insulin and glucagon are related. So what's the condition under which we're going to expect to see insulin secretion increasing? Okay, and click through. Okay, yes. So insulin is our hormone regulating the absorptive state. So the absorptive state is when we're well-fed, just eaten recently, and we're working on taking those nutrients and storing them into macromolecules. This other state would describe the post-absorptive state. So when you haven't eaten in a while, you still need to be up and doing stuff usually. So that is when we're going to be taking all those stored molecules and using them. So glucagon would be active in this other situation for the post-absorptive state. Okay. So our role of insulin, we're starting from the top. Insulin, absorptive state. What we're doing is trying to build up energy stores. So insulin is a peptide hormone. So it's like protein-based hormone. That's what a peptide hormone is. Hormones can either be made from lipids or from proteins, essentially. Okay. So insulin is a hormone. It's secreted from the beta cells in the islet of Langerhans in the endocrine pancreas. And its role is anabolic. Anabolic means we're building stuff up. Anabolic means to make something bigger, essentially. A metabolic process making something bigger. So in this case, we're building up energy stores. We're making nice big macromolecules, okay? So glycogen is our big form of glucose. It's lots of glucose strung together. So we're going to do glycogen synthesis in response to the presence of insulin, right? Insulin tells us store that glucose as glycogen. It also tells us take whatever you can get and also store that as fat. So we're also going to see triglyceride synthesis in response to insulin. All of this being associated with that absorptive state. Okay. It's also going to be telling the rest of the cells out in your body that it's good times, right? We've just eaten, so we can use glucose for energy. So we're going to be telling the other cells to take in glucose, right? So you can take in glucose, you could use it for metabolism, and you can use it for storage as glycogen if you happen to be a cell that can store glycogen. Catabolism is the opposite of anabolism. So we're going to see less breakdown of molecules. Catabolism would be breakdown of molecules. Okay. So we don't need that to happen during our absorptive state, because during our absorptive state, when we've just eaten, we're good. We don't need to break stuff down. We're trying to store up our extras. Okay. So we're going to see a decrease in any catabolic processes. Okay. So insulin secretion, it's happening during the absorptive state. So once your body notices that you've been eating food, right, it's going to start secreting insulin so that the cells know they should start storing that excess energy. So we're going to see insulin secretion going up and up and up during the absorptive state. Okay. So the triggers for that, right, what's happening here is that we're seeing, all right, we've got increased glucose in the plasma because your intestines just pulled in carbohydrates into the blood. You're seeing increased amino acids in the plasma because you just broke down proteins that were in your food, pulled those into the blood as well. Okay. Our parasympathetic nervous system is active because that's the rest and digest part of our nervous system. Okay. So parasympathetic nervous system active during the absorptive state. And we have some secondary hormones kind of produced by the digestive system. So there's this peptide called GIP, which is basically just a signal from your intestines telling your body that you have these products of digestion swimming around in the blood. So that's another signaling kind of thing. Okay. Then when we shift to the post-absorptive state, so after we've sucked these things out of the blood, stored them up, right? It's been longer since we've eaten, right? Then during the post-absorptive state, we're going to stop secreting insulin, right? Insulin was our trigger to pull stuff out of the blood and store it. During our post-absorptive state, we don't want to do that. We want to spend our energy, right? We're spending our money. So this is when we're going to see the sympathetic nervous system active. We're going to see epinephrine swimming around, and we're not going to see much insulin anymore. We're not secreting that. Instead, we want to secrete glucagon, which is going to have the opposite effect to insulin. So here's a flow chart of what's going on. So this is our absorptive state, right? So we're seeing insulin secretion go up from the pancreas, specifically the beta cells, during our absorptive state. So most of our tissues are going to be pulling in glucose. So glucose uptake is increasing. We're also pulling in other nutrients. So we're going to be pulling in amino acids, okay? And we're going to start storing molecules. So in many cells in the body, we're going to be making proteins. Proteins are just amino acids strung together, right? So that's our polypeptide, our bigger structure. We don't have to break down proteins anymore because we got amino acids to build new ones. So protein breakdown stops happening. In our adipose tissue, so your fatty tissue, you're going to be storing stuff as fatty acids and triglycerides. Lipolysis is the breakdown of lipids. So you're not going to do that right now. You don't need to break down lipids because you're focused on storing them up. In liver and muscle, we're taking glucose and we are storing it as glycogen. That's our big molecule here, right? So our storage molecule is glycogen. This next word is the breakdown of glycogen, glycogenolysis, right? Lysis should always tell you that that's breaking something. To lyse is to break apart, right? So breaking down glycogen, not happening during our absorptive state. That's why this is a down arrow, because we're making glycogen, right? We don't need to break it down. We don't need to harvest that glucose. In our liver, again, we're making some fats, okay? The liver is also able to make new glucose, but it doesn't have to do that when you've got plenty of glucose in the blood to start. So this word is gluconeogenesis. We did briefly talk about glycogenolysis and gluconeogenesis in, I believe it was our first unit, but it's been a while. So I'm just highlighting these words for you again. All right, so we're not making new glucose anymore, gluconeogenesis, because we've already got some in the bloodstream. We're just focused on taking all this stuff in, and we're storing lots of stuff as fats here. We can intro this quick. All right, glucagon, literally just going to be the opposite of insulin, pretty much. So instead of coming from beta cells, it's coming from alpha cells. Instead of telling cells that they can use lots and lots of glucose, it's telling almost all your cells, hey, don't use any glucose because the nervous system needs it. So the only cells that are allowed to use glucose during this state are our nervous system cells. It's going to mobilize our energy stores. So it's going to break down glycogen. That's the glycogenolysis. It's going to break down fats. That's our lipolysis. And since we don't have enough glucose kind of going around at this point, right, we're going to make new glucose and put that into the bloodstream so that we can send it to the nervous system, keep your brain functioning. Okay. So glucagon is a catabolic hormone, meaning it's telling your body to break stuff down. And it's the antagonist of insulin, basically meaning it's its opposite, has the opposite role. Its job is to tell the cells the opposite thing that insulin was telling those cells. Okay, so we'll stop there. And yeah, on Monday, we'll finish it out and briefly talk about the somatic nervous system before moving into our muscle.